Welcome to the last session, Commission J. Actually, yeah, it's last two sessions of last block. And I'd like to remind you that this session is recorded. And the next, the first talk will be again by Taylor, who will tell us this time about robust R2D2 for scalable radioinformetric imaging.
So, hi everyone, I'm Taylor again, and this talk is on behalf of my supervisor, Yves Will, and also on behalf of other members in our research group based in Edinburgh, Scotland. Oh, why does it always skip? So I'm first going to go through, introduce you to the R2D2 framework, showing how it is the AI version of Clean. And then I'm going to show you the enhanced version of R2D2, how we made it more robust to different observation settings. And then finally, I'm going to show you some other extensions of R2D2 for wide field and wideband and other types of imaging. So not only in radio astronomy, computational imaging is very in demand for high resolution and dynamic range for precision imaging. And the algorithms or the methods need to be robust so that it can handle uncertainty quantification and calibration. And both in acquisition and reconstruction, we want efficiency as well as scalability to a larger data volume. So we have the inverse problem here, y equals to phi x hat plus n again, where x hat is the sky image that we want to form from visibility data y, measured from process phi with some complex Gaussian noise n. And to get the image of interest x hat from y, we need to leverage some prior image model, and such model needs to be precise and robust. And again, with the next generation telescopes, we need the algorithms to be efficient and scalable to handle such large image size and data size. So most of you who's worked with radio astronomy should be familiar with CLEAN, but just to reformulate it in our way, we start with the dirty image, which is the back projection of the data, and which also can be seen as the convolution of the PSF with the image that we seek with some noise. And the clean iteration is basically alternating between the major and minor cycle, where the major cycle is computing the residual, deducting the back projection of the current image estimate from the dirty image. And then the minor cycle is peeling the points that we want to add to the reconstruction. And this clean algorithm is very simple. It's very efficient and scalable, but is limiting in precision and robustness. And so there are many radio interferometric imaging algorithms that have been proposed. And I'm going to show you our method, which is R2D2, standing for residual to residual DNN series for high dynamic range imaging, which consists of a series of DNN. Basically, we call it the learned version or AI version of CLEAN, because if you look at the blue box, the equation in the blue box is almost identical to CLEAN, where the only difference is instead of the peeling operator, now we exploit the current image model learned by a DNN. And the iteration structure of R2D2 is basically the sum of the previous image estimate and the output of the current DNN, where the input of the DNN is the residual from the previous iteration and also the image estimate of the previous iteration. And the residual, similar to the dirty image, is computed by the back projection of the data, which is the dirty image, deducting the back projection of the current image estimate. And in R2D2, we normalize this by kappa, which is the 1 over maximum of the PSF, so that the so that we have some normalization in the data for the DNN to work better with a large variety in the images. And we also have a series expression for the final output of R2D2, which is just the sum of all the outputs of the DNNs. And each of the DNN is trained with this loss function here. It looks a bit complicated, but it's just basically comparing the L1 difference between the ground truth and the current image estimate, which is the sum of the previous image estimate and the network outputs. And here's another way to see R2D2 just with arrows and boxes. So we start with the residual at the zeroth iteration, which is just a dirty image, going into the DNN with a zero image estimate. And then we get the output, which is which sums with zero. So it's just the output of the first iteration. And then we use -d, which is what we use as the operator to compute the residual. And then the residual and the first iteration output goes into the second network to get the second network output, which sums the first network output, and so on until we get to some kind of convergence. And so this was the R2D2 that has been proposed, and I think Eve also presented it 2 years ago in Sapporo in URSI again. But we've since made some enhancement to the model. The previous version, we used the well-known UNet, but we've since changed it to something that a new proposed architecture called UWDSR, where we replaced or we added an additional convolutional block between the usual two convolutional layer in UNet, and we call that UWDSR block, which you can see on the right of the screen is in the green box, is 16 layers of these convolutions with skip connection or element-wise addition. And another difference is we can reduce the number of channels required in UNet from 64 to our model, which is 32. So this model is actually lighter than UNet's. And for training our R2D2 to make it more robust, we have to make it more robust, we have exponentiated our training images, 20,000 of them, to a dynamic range of 10 to the 3 to 5 times 10 to the 5. And they're all 512 by 512 pixels. And we used 20,000 VLA simulated observations to generate the dirty images needed for training. And previously, we only trained it with Briggs weighting of 0 and super resolution factor of 1.5, but we've since expanded the range for Briggs weighting to be between -1 and 1, so that it encapsulates both natural and Briggs weighting and somewhere in between as well. And then super resolution factor, instead of just 1.5, we've extended it to the range between that and 2.5. And for validating the R2D2 method, if you listen to my previous talk, it's almost the same. Is with these 4 radio images, we formed 200 images, and we also exponentiated to some higher dynamic range. And we have the same observation settings as the training here. And here's the table comparing the performance of different algorithms. I've introduced clean and R2D2 and robust R2D2. In the second row, we have USARA, which is unconstrained sparsity averaging, reweighting analysis, and a pure optimization-based algorithm developed by our group. And then ARRI is another algorithm developed by our group, but it's also optimization-based, but instead of using the sparsity averaging regularization, we trained a denoiser to do that. So it's what we call a plug-and-play or PNP optimization algorithm. And then UWDSR is just the first network of the robust R2D2 series, which is an end-to-end neural network. And the first two columns, we compare the image quality metrics SNR, and also we compare them in log scale in log SNR. We can see robust R2D2 performs the best out of the methods. And then the third column, we have data fidelity, which is the residual to data image ratio, which is comparing the LP norm of the residual and the dirty image. And we can see the best one is USARA, but it's comparable to both ARRI and robust R2D2. And then the second last column, we have the number of iterations. And in this part, clean outperforms all the other ones. But if we compare the runtime of all the algorithms, robust R2D2 is around 10 times faster than clean. And because UWDSL is naturally the first term of robust R2D2, so it's a fraction of it. But you can see the performance in SNR and log SNR if we use just one end-to-end DNN versus the whole series that we've trained. And then another enhancement to R2D2 method we've made is instead of just deterministic output from one trained model, we've trained 5 realizations of the R2D2 series DNNs so that we can kind of simulate what Bayesian imaging do and collect samples from R2D2. And this allows us to quantify the epistemic uncertainty for R2D2 reconstruction. And in the middle, you can see the reconstruction of R2D2. It's not just the reconstruction, it's the average of the 5 reconstruction of the 5 realizations of R2D2. And then on the right-hand side, you can see the standard deviation of the 5 images divided by the mean image in the center. And then on the left, you can see the metric that we call mean relative uncertainty, which is just the average or the mean value of the standard deviation over mean image that you see on the right-hand side. So this is the first iteration, which is, or the UWDSL outputs. And then if we skip further to the third iteration of R2D2, we already see significant improvement in both recovering the faint emission and also the decrease in the uncertainty. And then if we skip to the 16th iteration, where R2D2 has decided to converge with some condition, we have significant improvement over the first and third iteration. And also, again, the uncertainty map has decreased significantly. And then we've also validated that on real data of sickness observed by VLA at S-band. And this is the dirty image. And then we have the clean reconstructed image, USARA, where you can see a lot of the reconstructed parts is kind of corrupted by artifacts from the regularization of USARA. And then we have ARRI, where you can see significant improvement from USARA, and it also shows a lot more details than clean. And then we have R2D2, which is not the average version of the 5 realization, but just one realization. And again, if I flip between ARRI and R2D2, you can see in this box where we show the reconstruction at the center. R2D2 is reconstructing this part much smoother or better than ARRI. And also the residual map is better as well. And then if we switch to the robust version, although we don't see significant difference in the reconstruction, even if we take the mean of the 5 realizations, it allows us to compare the uncertainty map so that we can be more confident with the reconstruction. And finally, these are all still work in progress, but we've also focused on wide field imaging, where we proposed a faceted R2D2. So with a larger image size, maybe 1.5K or even 4K by 4K, we can extract patches of the images and then fit them into the R2D2 DNN as channels. And we've seen that it still works as well as training R2D2 at the full image size. But as we all know, on GPU, if we work with larger image size, it's going to take a lot higher computational cost. So the advantage of faceted R2D2 is that we require less computational cost for similar comparable performance. And then we also worked on wideband imaging. This is this is still faceted, but in the matter of time. So this is spherical imaging by Ayub Tajar at EPFL, and these are results published in his paper. So if you're interested, you could have a look at his paper. And finally, we've also worked on wideband imaging with R2D2, which we call hyper R2D2. Again, we fit the dirty images and the current image estimate at different frequency as different channels into the DNN and train it as a series. And we actually find that this hyper R2D2 perform better than when we use R2D2 trained normally and fit the dirty images at different frequencies to R2D2 separately. And we also show the spectral indices of the reconstructed image just for reference. And to summarize, we are going to validate faceted R2D2, hyper R2D2, and the spherical R2D2 with real data and also improve them further. And we also want to add calibration and polarization functionality for R2D2. And another disadvantage of R2D2, similar to Sam's method this morning, is that R2D2 is trained telescope specific. It's not sampling pattern specific, but it's specific to the telescope. So we want to investigate if we can train that to make it work for more than one telescope. And yeah, so thank you.
Have time maybe for one question. And well, I asked. So it would be very interesting to see what would happen if you train the model on multi-frequency data and then try to process like monochromatic or the other way.
Yeah, so all the simulation and real data results, they are actually multi-frequency, but imaged monochromatically. Yeah.
Okay, thank you.
Thank you.
Thank you again. So the next talk is by Nikhil Gupta, who will tell us about machine learning frameworks for large radio surveys.
All right. Thanks a lot, everyone who managed to stay here after all the lunches and teas. So I'll be talking about some of the machine learning methods that we have been developing for these large radio surveys, which are collecting a lot of data. I'd like to begin by acknowledging the traditional owners of the land where I work, which would be the Noongar Nation, Wajud people of the Noongar Nation, and also the Gadigal people we are meeting today. To begin with, I'm talking about the radio survey. So this plot is a bit old, 2017 or plot. On the left, you see the different radio surveys. So you can see the EMU survey with the ASCAP there, with the large area coverage and also lower sensitivity. And similarly, VLAS, LOFAR, which are covering a similar amount of area, but different sensitivities. And if you look at by the date, 20 years ago we had NVSS and first survey, which in total detected about 1 million radio galaxies, and with EMU, for example, we're gonna detect around 20 million radio galaxies. And also because of the increased sensitivity, we are gonna detect more and more extended sources. So probably the total number of extended sources is gonna be more than the total known sources which we had 20 years ago. Quickly on ASCAP, several talks on ASCAP yesterday. It's located at Inyari Mana Ilgari Bundara, the Syro MRO observatory in Vajari country. It's about 700 kilometers north of Perth. It's equipped with phased array feeds, 36 antennas, 12 meter diameter each, and baselines up to 6 kilometers. So several surveys planned with the ASCAP. For example, these have been talked about here in the conference as well. I think Liz talked about Flash. We heard about the VAS survey also from speakers yesterday, and I think Andrew in the early morning talked about the EMU survey. So in this talk, I'll talk about the methods developed mostly for the EMU survey, but give you a little glimpse in the end for other surveys as well. Okay, so EMU survey is gonna detect like whole southern sky. This is the plot and the coverage you see in the blue until July last year. So July 2024. So there will be 10-hour observations or 5-hour observations. And then there'll be the sources which will be detected are up to 0.2 millijansky per beam. So we're gonna go very deep. And with all these surveys and with EMU survey and ASCAP survey and then different telescopes coming up, we're going to detect a lot of data. So data rates, if you compare with Facebook, Google, ASCAP is almost about Google per year data collection. And then going to the SK or DSA 2000, we're going to have a lot of data. So what we're going to do with all this data, we need to find better ways to analyze data, to process the data, and to also, after pre-processing, to make sense of the data and do science with the data. So I think the MLAI is going to be very important in the coming years, because we are in the very big data arena with the radio telescopes and astronomy in general. So I'll begin with very quickly on different kind of machine learning methods. Supervised learning, where you have all the truth labels available. Self-supervised or unsupervised learning, where you don't have any data available, but you make sense of the data. So the machine makes sense of the data on its own. Then you have weakly supervised learning, where you have some truth labels available for all the images. And semi-supervised learning is that you have some information available, for example, for some part of your data, so some part of your images. There are different kind of labels. So class labels are where you have information about, if there is a dog and cat in the picture. And then there are pixel level labels where you have like boxes, segmentation mask, or instant segmentation where you have different objects colored in different masks as well. So what do we do with all this radio data? So for example, the picture in the background is from the EMU pilot survey. And there are a couple of things that I think is very interesting as a national science agency to provide the data to the users to do the science from there. Is to get the catalogs right. And also like we are the first people who are going to see the data. So it makes sense to also discover new radio phenomena when we have the data. So start with the detection. I think the problem, like I mentioned, with the ASCAP survey, we were going very deep. So we're gonna detect a lot of extended sources. And the sources like this, where you have three components, A, B, C, and C, the algorithms like Salavi or Asian, they're gonna say that, okay, these are probably three different radio galaxies and put them in three different boxes or in three different positions in the catalog. But that's wrong. This is one single FR2 galaxy with the host in the center, and they should be put in like one single galaxy in the catalogs as well. And we're gonna have like millions of these in the EMU survey alone. So starting with that, we developed this radio galaxy net dataset where we manually basically looked at something like 3,500 extended radio sources from the EMU pilot survey. And people like Ray and Hines and other senior people also looked at the data in great detail. Where the data, we have like classification labels, we have bounding boxes for these extended sources. And then we have key point where we have the positions of the host galaxy in the infrared picture. And these are all the data is available now in the JSON format, so you can directly use it to train your models. So this is an example of a model where you inject the images. So we can do it with the FITS images as well. So directly putting the FITS images to the model, it makes sense of, so it looks at the images in different, with different criteria in a similar way the human will look at them. And then there are transformer, encoder, and decoder, which give you predictions about the boxes, put the boxes on these extended sources, and also the host positions. So just very quickly, transformers are a bit better because with the CNNs, you have a window function, which goes from top left to the bottom right. But it has usually a 3 times 3 pixel or 5.5 pixels. But transformers are a bit better because they make sense of the whole image as a whole, depending on the memory of your GPU. And this is shown here in this graph. I won't bore you with all these numbers, but the top plot, the top table is for different transformer networks. And the bottom one is for a couple of networks using the CNNs, and the difference is about 12%. Also, all that thing is with the supervised learning, but you can also do semi-supervised learning with different networks where you don't have all the information in the image, you have partial information, but the model can predict the information which was missing in the image. So this is just an example of semi-supervised learning. So our best performing model we call the Galdino model. It basically we found out that if you look at the central source, the fraction of sources with intersection over union greater than 0.5 is like 99%. Which is really good. And we use that model as a backbone model for our RGCAT pipeline, which is the catalog construction pipeline. So I won't go through these details of this, but give you an idea of what the pipeline does. So for example, you have these bounding boxes placed on different detections in the maps. You have this FR2 galaxy, and there are point sources close by. So what the pipeline does is to take away the high score sources first out of the picture and delete them from the older catalog. So the first source here will be with the score of 0.8, the pink one, then the green one with 0.6, and then score of 0.5, which is the remaining stuff in that box, which is the FR2 galaxy. So this whole thing is gonna give us 3 different radio galaxies. And that's the idea behind the pipeline, basically. We have been running these pipeline now for the EMU main survey. We have like 400 observations. So the catalogs are there for more than 7 million radio galaxies. And there we have like all the information from the radio. We have infrared information. And wherever available, we have the information about the redshift from the DES survey and the DAISY catalogs. This is something that I just added in the morning. I was talking to someone about the class activation maps. So it's also a detection method, but it's like a magic because in this one you are not given in the supervised learning. You gave like boxes and all the information to the machine to learn from. But here the only information available is like the class label. Which is the top source is the FR2 and the bottom one is FR1. So that's the only information given to the machine. And the machine makes sense of where the source is, what is the shape of the source, and predicts the mask around that. I think so. One of the use for such systems Okay, missed the slide there. But could be in the citizen science kind of projects where labels are there, but you need to get the bounding boxes, or you need to localize the sources, detect them, and catalog them. So this is an example also, if it doesn't matter if the source is in the center or it's near the border, it detects the source, and you can see even the shape of the source is detected, and none of this information was given to the machine, and it all works because the model is trying to predict the class, and in order to do that, it's basically trying to find out what makes it to classify something as one source or one class or the other class. So these are the CAMs. I think was discussed earlier in this session as well. Okay, this was the slide I wanted to show that these systems can be used with the citizen science. Okay, moving on to the second thing is the discover new things. So this is an unsupervised way of doing these things. You have all the images from the EMU survey with a given cutout size in a box, and you push them to a SOM network, self-organizing map. It organizes itself. You have like the non-sources all collected in different boxes, but then you have some sources which don't belong to any of these boxes in the SOM letters. So those sources can be looked in detail to find the peculiar sources. And one of them we rediscovered using the machine learning method, which was first found by in Norris et al. Is the odd radio circle, which got pretty good press attention as well, and still a mystery that still trying to find out what these objects are. And also some other peculiar objects which were there in the pilot survey. In the main survey, we basically tried a slightly different technique of using the supervised learning to tell the machine that, well, these are the kind of the things that we are looking for as peculiar sources. And it's definitely not the FR1, FR2, or the normal kind of radio sources. So it came up with using like starting from for 4 million radio galaxies, only 1,700 radio galaxies which were needed to be visualized by humans. So among those 1,700 sources which we visualized, we found more odd radio circles in the main survey. So now I think the total sample size of odd radio circles along with this is more than 10 or 11 such sources. Then we had glares. Don't ask me about the full form of the glares. Can just have a look at the paper. I don't remember the name myself. But these are the sources which we think could be the precursors or could be one of the evolutionary stage of the odd radio circles. So in the direction of understanding what odd radio circles are or how they are forming. And then there are very interesting star forming starburst radio ring galaxies, SRRGs. And special thing about these is that in the radio image on the left, there is nothing in the center. So the radio emission is missing in the center. These are resolved galaxies, so you can clearly see in the optical these galaxies are there, but there's missing radio signal in the center of these sources. So still trying to understand what causes such a thing. Wanted to talk a little bit about the foundation models. So these are basically self-supervised models, the models that you see in real life, like the ChatGPT or other stuff. These are basically all the self-supervised models. So what we did here is like develop an app to catalog different kind of sources which users could be interested in. So for example, starting from a self-supervised network trained on a huge data set, something like 2 billion image text data set from real life. And using that model, we fine-tuned on our radio data and got all the images from the Casta and created embeddings for those images. So reducing the size from, like the images which are about 300 gigabytes to just 300 megabyte in the form of these embeddings. And that's all is used like the fine-tuned model and 300 megabytes of embeddings and some metadata about the positions of these sources. So this is another way of, reducing the size of the data. And you can have a look at this app. It's online as well on this link. So you can try to find sources in a couple of ways here. You can upload your favorite radio galaxies or some different really peculiar things that you are interested in. So for example, here I just uploaded a FR2 galaxy and asked it to find all similar sources in the EMU survey. This is for the first year of the EMU survey, and we are updating it as we are getting the observations. And the catalog gives you all these similar FR2 sources. So a very interesting thing is that even the orientation of these sources is very similar. It's almost similar orientation. It's just the flip due to the MATLAB, but it's similar orientation. And also the other way is that by textually you can ask the app to give you all the sources. So for example, here I asked for give me all this catalogs of give me a catalog of band-tailed radio galaxies. So it gave me a catalog of that. I can change the probability, the score to which I can trust. And then I think with some 200 sources, you can see that the top, all these sources are pretty much band radio galaxies. So there are other things that there are ideas that we are developing or working on. First thing is like making this Amuse app even more workable or more usable with the more data, optical and spectral data, and of course adding more and more EMU data as it comes in. And also improve on the text-based prompts using the large language model, because at the moment it's just the usual the small text model which is used in this one. There is Radio Lava where the problem is flipped. So basically, it's more can be used for educational purposes. That given an image of a radio survey or radio image, you can talk to the model, you can ask answers and questions. So it's more like a chat kind of thing. Simone recently put a paper on this one, which is accepted now. Then there is image reconstruction. Sam talked about it, and reconvolution and ML clean as well. I think the previous talk was very similar to what we were thinking. And removing bright source artifacts in the imaging, which is also something that can be done. There is RFI detection and removal, detection of H1 sources. So Lee has a poster outside. You can have a look at. It's trying to find out the false detections there. And then data compression, and there are other things that we are thinking of doing with the similar techniques. So I'll leave you with this summary and just say that the big data era is here, and we need better solutions to how we think. Thank you.
Questions?
Yeah, thank you for this nice talk. I had a question about the multi-wavelength counterparts, which you mentioned briefly. Of course, one of the reasons for associating these components is so that you can pinpoint the optical galaxy. But it needs to be done quite accurately because the surface density of optical objects in the sky is quite large. And I'm just interested to know what your experience has been so far, whether you've tried to automatically identify the multi-wavelength components or not, and how well that's gone.
Right. So I think, as you said, it's a very tricky thing to do, because even for us, when we were doing it manually on this radio galaxy net data, it's very hard to say because of the density of these sources in infrared, or in optical, it's even higher. That which would be the right host. And I think the idea here is that to identify a few hosts around that source, which could be the right host, and then try to do it a bit in a probabilistic way using the colors, which is still not implemented here. But this is something in the direction that we are thinking, that to add basically more optical information in there in order to find out that which could be the right host, and which even like humans are always confused. So Heinz thinks that the right host is something completely different than what Gray thinks. So this happens a lot. And one of the reasons that the paper with the manual it took like 3 years to do, because we can't easily make decisions that which would be the right host galaxy, and I think we're still not there.
Well, let's thank Income again. And the next talk will be by Wasim, who will tell us all about ASCAP's polarization.
All or not, I'm not sure, but certainly touch upon a lot of what we're doing currently at ASCAP in terms of polarimetric images. So a lot of observations have already been done. So this is data collected straight from CASDA using data that's publicly available. This is done in collaboration with Jennifer West from the Dominion Video Astrophysical Observatory in Canada. All right, so I'll briefly give you an overview of what radio polarimetry is about, slightly touch upon ASCAP. You must have heard a lot about ASCAP in the last week, in the last couple of days, so I won't dwell on that. And I'll show you some current findings from some 500 odd days of observations from survey science teams like EMU and POSSUM. All right, so ASCAP is an interferometer with 36 fully steerable dishes. The novelty in ASCAP are primarily two. It's wide field of view facilitated by the phased array feed and a mechanical axis, roll axis that allows you to keep the footprint of your beam constant in the sky. So these are two key design decisions that went a long way in letting us make high dynamic range images, both in total intensity and in polarization. Needless to say that these complexities add lots of overheads when it comes to calibrating the instrument. So this is how the signals are sampled at the focal plane of the dish. What you're seeing here is the phased array feed. So it's an array of detectors, 188 of them, half of which is polarized in the horizontal direction and the other half polarized in the vertical direction. So you have full polarimetric recording ability. So if you look at the cross section of a path, those 188 elements are something like are arranged in a layout like this. So what we do, or what this allows us, is to manipulate the electronically the gains of each of these elements to form beams. So ASCAP, the dish of the ASCAP, the aperture is circular. So if you look at a point source, the electric voltage pattern at the focal plane should look like an AV disk. So you point your telescope towards a bright source. In our case, it's the sun. For a single dish, it's still a point source. And then you measure the voltage response at each of these individual elements. And depending on how much it deviates from a theoretical AV pattern, you can adjust electronically the gains of these elements to make the beam pattern look exactly how you expect. So this is the first step of calibration. We call this beam forming at this stage. And you can form beams, different beams. Essentially, these different circles are actually looking at different or receiving signals from different parts of the sky. So lots of flexibility that allows you to form any kind of beams theoretically that you would want to. Okay, what does this help us achieve? So it helps us achieve huge field of view, large field of view. That makes ASCAP a very fast survey instrument. So just for a comparison, traditional telescopes like the ATCA, whatever ATCA takes to, this is a huge, large piece of the sky. It's a beautiful galaxy, Centaurus A. The ATCA would require about, I don't know what's the number I have put up there. So 1,200 hours of observing in order to cover this region. ASCAP can do it in 10 minutes, thanks to these novel technologies that ASCAP is equipped with. All right, so now that I have introduced ASCAP, new technologies, new challenges, so you need to calibrate the instrument too. I won't go into these details. ASCAP is an interferometer. This is the measurement equation. What is it that we are measuring? What's key here, I think, is to show that the take-home message is the signals that comes from sky, signals that are astrophysical origin, they pass through the medium. They pass through the local atmosphere or the Earth's atmosphere, for example. Then they're received by the the PAF ports that has got electronic components like gains. So these are the dipoles, they're the PAF ports. They have gains. So each stage, each component that we have introduced to detect the signals adulterates the signal itself. It pollutes the signal. And so we need to calibrate in order to be able to talk about or retrieve the original original signal that came from the sky. We don't have to go into this detail. This is just a cartoon of what I already said. So two primary effects. One is this is the ionosphere, a model of the ionosphere, just a cartoon of it. And then the feeds, and then we have leakages. So what we think of as horizontal may not necessarily be the horizontal electric field. Some of it leaks into the vertical detector and vice versa. So there is leakage of one polarization into the other, which you need to calibrate. And then the instruments gains, the amplifiers, you need to amplify the signal. That adds yet another stage of corruption that you need to characterize. So without going into the details, all I'm trying to say is this model can mimic any kind of transformation that your signal undergoes while traveling from the sky onto your recording device. Okay, this is yet another cartoon of the different polarization specific calibration that we had to care for. The feeds in ASCAP are linear, so horizontal and vertical electric feeds, but they could be distorted. So you need to characterize that. Okay. The ionosphere, I'd like to mention here, the ionosphere introduces, it acts like a refractive index medium. It introduces differential delays between the X component and the Y component, and you need to characterize, well, not just X and Y. Anyway, it acts like a refractive index medium. What you think of as the delay between the signal detected by one antenna, it's not just the geometric delay. The ionosphere introduces yet another refractive index based delay, which you need to characterize. The trouble is we do not have ionospheric measurements, the tech measurements real time. So this is yet another form of complication that you need to worry about. I'll come back to it later when I talk about the results. So now just showing you what it is, the different stages of calibration. So we need to calibrate the bandpass of the system. When you just look at the antenna gains, usually they're like this. So after you calibrate, the goal is after the calibration, a source that has a spectral index or spectral behavior like this, an SED of this pattern, you should be able to retrieve that. So this is a SED on a known calibrator, and a demonstration that after having applied the right calibration on your antennas, you have been able to receive, or you will receive, you'll be able to regenerate the bandpass of the system. So this is the first stage called primary calibration. It's not enough because these things change with time. So you also need to address the time varying gains of the system. So it's done for ASCAP. Matt discussed about the pipeline. We derive the time variations using a technique called self-cal, which is quite popular in radio astronomy. So self-cal allows us to characterize the system gains as a function of time at a cadence that we decide appropriate. The goal initially was to be able to use an on-dish radiator at the vertex of the dish. It's a synthetic calibrator of known power, known properties, and we irradiate all your PAF elements. These are the gains of the PAF elements that varies as a function of time. They're very small variations, yet critical, and so you need to characterize them. So the goal was to use the ODC to correct this on the fly as you observe. However, the on-dish calibrator system introduces its own noise. So it doesn't just radiate onto the PAF elements of that particular antenna, it radiates some onto the nearby antennas as well, thus polluting any signal in short baselines, which is critical for doing some kind of studies like diffuse polarized emission, for example. So ODCs had to be turned off while you're observing, but are used occasionally to update your system gains. Not just that, so we had time, we had frequency. We also need to calibrate our instrument as a function of look distance. So these are called the beams. So ASCAP has 36 electronically formed beams. All of those beams in both XX and YY polarization needs also to be calibrated. So what we do for this is essentially place a known calibrator at different parts of the beam, like raster scanner bright source, an unpolarized bright source in our case, and derive the system properties as a function of those positions of the beam. So that's how we characterize the primary beams of ASCAP, all 36 of them. It's a huge overhead because we have to do this for all 36 of them. In a sense, this signal from the sky, I have modeled it as, well, I did it something here. All of us would know that Stokes V, or the circular polarization from the sky, is usually very feeble. This is true for almost all directions in the sky. There are exotic sources. I'm not talking about those. But this is the true source property. It gets transformed by, so your signal can be represented in the Stokes formalism. It can be represented as a 4x1 matrix. So any transformation to a 4x1 matrix can be totally captured by a 4x4 matrix, which is essentially called the Mueller matrix of the system. And what you get here is the measurement. So you measure I, Q, U, and V, which is a representation, which is the original signal transformed by this matrix. So the essence of the entire exercise is to be able to derive these 16 elements. Not all of them are independent. So essentially, there are only 7 independent elements. I'm not going into the details again. The exercise is to be able to calibrate or find out all these 16 elements and go from what you measured back to the true property of the source. All right. But do we do that? So no, I'd just like to emphasize that all our calibration so far is done with only unpolarized sources. So you have I, but the dp, which is the degree of linear polarization, is 0 for our calibrator. So you won't be able to characterize any but the first 4 elements, the first column of the Mueller matrix, just so that we know what it is we are characterizing and what it is we are not characterizing. All right, so this was a measurement done before full survey science began. This shows the typical how. So I don't know how to go back. Is this back? The red button. Okay, so this is the Mueller matrix. If you use an unpolarized source, you just get this. So M11, M12, etc. are the Mueller matrix elements. So here, what I'm showing are the measured spectrum for those Mueller matrix elements, the first column, second column, third column. The fourth column I could not get because we don't have a known, we didn't use a source with Stokes V. Anyway, so this is how on the bore side, the on-axis instrument looks like in terms of how much the net corruption is. Repeating the same thing here, showing what it is that we can calibrate and what it is that we don't calibrate. So for example, this would introduce, if they're not calibrated properly, they introduce a rotation between the Q and U, Stokes, the linear polarized vectors. So how much is Q and how much is U? We can. All right, so this is the result after having applied the calibration on axis. It looks pretty good. I mean, this is a very good level of calibration, 0.04%. This is to show, so the movie is showing you how the beams in one of the polarization looks like for different beams. So these are all 36 beams. So these are measurements we actually do using holographic methods and derive the leakages of Stokes I into, here I'm showing just Stokes Q. And so this now comes the result part. So this is the same source seen by 4 different beams, and using the measurements from holography at those locations, you can see that the same source appears at different parts of the beams. So when you apply the holographic corrections, you can see that the measurements, which are the scatter plots, and the solid lines, which are actually the model from the holography, they match very well. So this was an unpolarized source, and the residual for all of these sources in all of the single beams come out pretty close to zero. But this is just showing that our holography is doing great for unpolarized sources, or characterizing leakages of unpolarized sources. Essentially repeating the same thing in this slide. So here, I think something got missed, but that's okay. So now with the data available on CASDA, so almost 500 days of observation are available on our data archival system. It's time to see how we did. So we grabbed the data from CASDA and plotted for each SBID, which is the identifier for each day's observation. We plotted how the degree of polarization for unpolarized sources. So we had some criteria so that we filter out the polarized sources, how the degree of polarization varies as a strength of Stokes I, and the asymptote, the value of the asymptote is a rough estimate of how well you did. So if you looked at a single SBID, the typical value of the leakage of I into the linear polarized Stokes is about 0.2%, which is again a good thing. And this is not just on axis, this is off axis too, including all sources. The same thing now, if I combine those data for all measurements, initially we had some higher leakages that got fixed. And after the system was upgraded, we could get consistently low for each day. We could see polarization leakages of 0.26%. When you combine all this data together, when you plot all of it together, you can see that you're getting less than 0.1% spurious polarization, leakage of I into other Stokes, which is really reassuring. And if you look at the distribution of these leakages as a function of the individual beams, you don't see any pattern, but this is not surprising because we do use only the central parts of the beams. We don't use sources that are far away from the center of each individual beam. So that looks really nice. Once again, close to 0.1%, 0.2%, much less than 0.2%. Now, as a function of the mosaic itself, as a footprint itself, the same thing, slight trend increase at the edge of the mosaic. Again, not surprising, but the overall value is much smaller. And I think these are my last slides. So all of these efforts that went into characterizing the system and correcting the data by has gone into producing science. This is one of the recent papers by one of the students working on this. And yes, it's facilitating great science. So with this, I would like to end my talk. Thank you.
Thank you. Questions? Everyone is stumped. I thought I'm not allowed to ask that question, but I'll ask one. Do you feel any effect of pointing errors?
In this, probably we have not gone into the details of those. So all we have done is taken really bright Stokes size sources. I don't think the pointing errors will be revealed by the kind of analysis we did with the kind of data that's available with us. But that's work in progress. And yes, the reports do have information about how much they are between different beams, what's the position offsets. There is data. I have not just showed it here. That would be something that we are working on. Yes.
Okay, let's thank Wasim again.
Thank you.
So the next talk is by Andrew Zick, who will tell us about visibility-based implementation of fast-folding algorithm.
All right. Great. Okay, thanks so much to the organizers for this opportunity, and also thanks to everyone who's here. I recognize it's definitely late on in the meeting, so thanks for coming along. So yeah, my name's Andrew Zick. I'm at the Australia Telescope National Facility, and I'm here to speak about efficient periodicity searches in the visibility plane using interferometric data. So I'd like to begin by acknowledging the Gadigal as the traditional lands of the as the traditional owners of the land that we're meeting on today, and pay my respects to their elders past and present. So periodicity searches are a widely used technique in radio astronomy, primarily used to find things known as pulsars. These are rotating neutron stars, incredibly dense and magnetized cores of exploded stars, which have a wide range of applications in astrophysics, from probing the interstellar medium, finding gravitational waves, and studying matter and electromagnetism in extreme conditions that cannot be reproduced in terrestrial laboratories. So what I'm showing here is sort of the population of pulsars. It's known as the PP dot diagram, or the spin. It plots the pulsars and their spin periods and their spin down rates on the y-axis. So there are a range of different populations you can see here. The canonical pulsar population live up here, have periods of about half a second. Millisecond pulsars, which have essentially slowed down over a long time and then been recycled via accretion from a binary companion, live down here. And these are the ones we can use for things like gravitational wave astrophysics. So it's been an interesting time in this field in the last few years, because this diagram, which looked like this for about 3 decades, has been moving towards something that now looks like this, where you now see we're beginning to populate this much longer period timescale on this diagram. Now, it's not clear whether all of these objects that are now being discovered are neutron star origin. Some of them will be, likely a lot of them won't be. But nonetheless, it shows this new parameter space that's opening up, and that we're just beginning to touch on the astrophysics that we can do with this. So the key question that lies here, so this line you can see here is known as the Death Valley. It's basically this theoretical model for where we think, how fast we think pulsars need to be spinning, and how quickly they need to be spinning down for them to produce this radio emission. So this is based on a range of different things, and so where objects live inside this parameter space tells us will provide new constraints on these sorts of models, and tell us a little bit about astrophysics. Okay, so pulsars have been found at timescale periods of ranging from milliseconds to seconds, but finding them at longer periods at above about 10 seconds has traditionally been very challenging. What I'm showing here is a time series of essentially power from the Parkes radio telescope, and you can see on timescales of about a second and longer, you're not really able to form a stable time series data to do periodicity searches on. So your period search techniques, which are largely based off FFT analyses, are going to be polluted by all of this red noise, which is due to a range of things: electronic gain variations, side lobes, and so on, spillover, and the like. Interferometers offer one solution, and we've heard a range of talks this week about that have touched on this. So what I'm showing here is some work from a long time ago, from 2019, showing some nice periodic pulses, not from a pulsar, but from an M dwarf. And the thing I really wanted to highlight here is how stable the time series is in total intensity over many hours. And that's due to our ability, this was taken with ASCAP, that's due to our ability to do a few things. Things like create a model of the sky and subtract it, self-calibrate the gains of the antennas. And that is those sorts of things really make us able to produce a nice sort of spectrally white time series that we can use to search for long period objects. It's also evident just in the way, if you look at what telescopes, what facilities have discovered these things, all of these long period things have been discovered through using interferometers. Okay, so typically beamforming based approaches or single dish data sets have been preferred over interferometric data products for doing high time resolution searches. And there's good reason for that. That's mainly because the data rates are very, very large. And so a single dish telescope gives you a single pixel, or a multi-beam feed might give you a few pixels essentially. And you can basically allow yourself to work at the resolution of what your computing gets you to. So that's really the one main reason that beamforming has often been approached over standard visibility-based approaches for finding periodicities. But with the advent of modern fast imaging systems like Krakow and ASCAP, the DSA Spotlight as well is doing post-correlation beamforming. This wall between what has traditionally been called the time domain data and the image domain data is at least moving around, if not sort of crumbling. So as I mentioned, the visibility basis, this UV plane offers some nice benefits. One of them is that if you work in the UV plane, the UV plane is naturally sparsely sampled by your interferometer, just due to the way the interferometer fundamentally works. They also work fundamentally on cross correlations. So you remove a lot of that red noise fluctuations that you get in traditional beamform data, and it allows you to model and subtract models of the sky, so you can further improve your data set and sensitivity to long period sources. Just to motivate it further, I think Danny Price showed an almost identical plot the other day. If you try and work out how many operations you need to get from taking a voltage with an antenna to getting some candidate at the end, I think Danny was talking about FRBs, I'm talking about pulsars here. And you sort of do the sums, you can work out that for any array with a sizable number of antennas, more than about 10 or 6, and a decent resolution, you're almost always better off doing visibilities. And that just essentially comes down to your ability to, instead of forming a beam for every pixel in your field of view, you're able to exploit the n log n efficiency of an FFT when you're doing the imaging part of the problem. So for things like Meerkat and SKA low, it's sort of a factor of 10 improvement over a traditional beamform-based approach. For instruments like DSA, you're starting to get into serious orders of magnitude improvements in the number of compute, at the expense of needing a high throughput at the very beginning of the problem, which I can touch on later. So how does it work in this UV plane? I should mention a lot of these movies were made by a student I was working with last summer. So this is sort of an illustration of what's going on here. So as the sky moves overhead, the projected baselines of your interferometer change orientation. So if you're just looking at one cell in your UV plane, it's going to get filled in this sort of sparse way, as you can see on the right. That's okay. If you're doing an FFT, this would be horrible, but there's ways around this using what we call the fast folding algorithm. So if we do this, if we take a time series for every pixel in this UV plane, we'll end up with something like this. This huge array in the middle is basically just UV cell versus time. And if you zoom in, you can see the time series that get filled in there. So it's a relatively sparse time series for every UV cell. So the idea is that what we're going to do is take those time series for each UV cell and apply this thing called the fast folding transform on them. This takes a time series data, essentially works out some drift rates and transforms it into a block that gives you trial period and trial phase. And then you can basically look for signals in that space. It works in a very similar way to the fast Fourier transform, was invented around the same time as well. So the steps here, the steps for how this would work would be to, if you're doing this on longer timescales, you could subtract the sky model from the visibilities, grid the visibilities for all integrations, possibly including de-dispersion, depending on what your search parameters are. And then you just perform this periodicity search along every UV cell. That'll give you a 4D cube of UV period phase. You can FFT each period phase trial, and that will give you an image for that period and phase trial where you can do a source search, and basically it reduces to almost like a transient search problem. So you're essentially forming an image-wide periodigram. So just in terms of implementation, we're trialing this now with ASCAP data. So this movie is made from a 10-hour track on ASCAP from the EMU survey. We're using the W gritter for gridding to handle wide field effects, which are important here. Using a library called Riptide, which has the core implementation in C++, wrapping that around in Python and parallelizing it with Dask. And the outcomes are that we should be able to find the location and period of unknown and faint periodic radio sources at any time scale. If you just image every time step as well, you can look for fast transient and upbeats as well. So here's a proof of concept. This is sort of the base case. So this source is called ASCAP J1832-0911. It's a 44-minute period, long period source, which was discovered by ASCAP and concurrently by an instrument called DART as well. It's 44-minute period. It's incredibly bright, at least in this observation, several Janskys. It's pulse flux density of several Janskys. What I'm showing here on the middle and left are the output gridded visibilities as a function of trial phase bin for the correctly recovered period. Then the right is, if you FFT that, you get the resulting image. So essentially, this is a image-wide pulse profile for those who speak pulsar astronomy. So what you see is that at a certain pulse phase, the sort of left-hand side of that image lights up as the pulse goes off. And that's the result of folding about 10 different pulses on top of each other. So we've recovered it, and we've shown that it sort of works. So we can go another step, try something a little more challenging. This is a source called PSR JM901-4046. This is a 76-second period pulsar that was discovered initially with Meerkat by single pulses. And what I'm doing here, instead of showing you images as a function of pulse phase, I'm taking the maximum signal to noise over all pulse phases and then showing you the image as a function of trial period. So I think I've already spoken over it, but essentially at the right period, which is 76 seconds, you see a source light up in the middle of that cutout there. And the resulting signal to noise at the source location is given in that periodogram on the right-hand side. So I'll just wait to give you another look before I move on. There it goes. So it works. So yeah, that's all I have. So we've demonstrated that this technique works. Through the use of those visibilities, the method overcomes limitations all the sorts of limitations you get with single pixel pulsar search methods like beamforming or single dish. You can apply to arbitrarily long and short period searches as long as you can handle the throughput that you need, or if you can store baseband data at whatever, to work with whatever time resolution you like. So the end-to-end computational cost of this method can be orders of magnitude better than a beamform approach, particularly for large N arrays. So that has obvious implications and considerations for new modern large N array instruments. But like I mentioned, the ability, it really relies on your ability to process and to throughput visibilities on a fast enough timescale. Currently, that timescale, I think, is at about a millisecond based on modern GPUs, but I suspect that will continue to go down very quickly as computing power continues to get better and better. So I'll finish there and take questions. Sorry, not a great talk for Friday afternoon.
Oh, yeah. So, yeah, well, it's interesting. Have you thought about handling W term in any different way? I understand because you're folding across like long period probably will not work, but maybe there are some tricks.
Yeah, it's a big problem to overcome. Essentially, not too much at the moment. I mean, I'm using existing tools to get around this at the moment, but it would be nice to have a way to just bypass that and have our own custom, really fast implementation that handles W corrections. So I'm keen to speak to people that know more about W corrections than I do.
Anyone else?
Yeah, I mean, on the W corrections, I mean, the array is instantaneously coplanar, so that might be something that you can exploit for this, given that you're probably not having a huge amount of rotation over the sort of periods you're looking for. I mean, if you're looking for something that pulses every hour, then the Earth rotation during the pulsation time might begin to be an issue. But if you're looking at something that's pulsating every 10 seconds or something, and you've got to put straight at 10, and maybe the W turns don't matter as much. You've compared this to beamforming, so how does it compare with an imaging approach?
Very similar. So if you just, I mean, essentially, sorry, let me go back. I think you just swap, sorry, I think you'd swap like step 2 and 3 here for that. And essentially you get a factor of whatever the sparsity of your array in the UV plane is, you save that. So instead of having to, because you have the same number of pixels in your image as you have in the UV plane, so you save at least a factor of 2 for most arrays. But as you go to something like DSA or a SK core station, you might not be you might not have such an advantage.
So
it's still much better than beamforming though.
Right. Yeah. Does the fact that you have more sparsity in the UV plane for each instantaneous frequency compared to the sort of multi-frequency case, so does that actually help you here because you're getting more sparsity for a given frequency?
I think all the grids I showed you are sort of multi-frequency in a way here. And I think you would do this with de-dispersion. And I essentially think you'd always have multi-frequency grids. I'm not quite sure how, I mean, maybe. Essentially, if we did this channel by channel,
okay,
maybe.
So maybe that's what I was getting at.
Yeah.
I hadn't thought about, I was assuming you were doing dispersion, but at this point you're not.
Yes.
But maybe that's not so much a problem if you're targeting these very long period things where the dispersion measure may be quite small compared to the pulsation time.
Exactly. But if we wanted to, Keith has implemented this for Krakow, basically de-dispersing baselines before gridding.
Right.
But it's a bit complicated. So I haven't done that yet.
Thank you.
Okay. No worries. Well, we'll have time for one more question. Anyway, thanks, Andrew.
Okay, great.
And so the last talk for Commission J goes to my co-convener, Stefan Weinholz, who will tell us about improving scalability and computational efficiency of self-calibration and imaging for low-FAR NST.
Yes, thank you, Max, and thank you for hanging around until the last talk of the Commission J program. So this talk is a talk on behalf of a team of people. They are listed here. They were an SKA development team. It has been reorganized a little bit in early this year, and now I lead both the team working on the self-calibration imaging pipeline for the SKA, as well as the one working on the Raptor pipeline, which is the self-calibration imaging pipeline for LoFAR, towards LoFAR 2.0. So what are the challenges for a self-calibration pipeline? Well, we have to deal with large data volumes. It was already brought up with the installed YASCAP talks, also terabyte scale data set. For each single LoFAR observation, meaning the old LoFAR system, we're now upgrading it to LoFAR 2.0, which will provide a factor 3 more bandwidth out of the stations. But even for LoFar 1, it was already 5 terabytes per observation. At these low frequencies of LoFar, you have to handle directly dependent effects, and also for modern disk-based systems, to achieve high dynamic range, often corrections for directly dependent effects are required. What's compounding the problem, especially in terms of computing resources needed, is that LoFar has international baselines up to something like 2,000 kilometers, really spread across Europe. And if you want to make a full field of view image with those baselines, you'll get images of the size 100,000 by 100,000 pixels. This will be more or less also the standard imaging size for the SDA bit system. And this leads to several issues. First of all, when we made the first image of these that I showed you on the previous slides for the International LoFar Telescope with the full field of view, that took several months of number crunching on a compute cluster to get to that point. Total at that time was 250,000 core hours to make a single image. That's obviously not good for your time to science. You basically throw your data in a supercomputer and then, you go off for 3 months, do something else, and then you hopefully get a nice image. Not really going to work. The other issue is that if we look at what are the costs for storage and compute for LoFar, and we continue business as usual, so meaning business as we did for LoFar 1, then by 2030, Aston will have to cough up 5 mega euros a year to basically just pay for storage and compute of LoFar data, which is not really sustainable for a single institute. If I scale up those numbers to SDA size, taking into account the expected data rates of the SDA and the expected compute needed for the SDA, that means that the SDA, including the SRC network, would have to cover up 300 mega euros a year, which I think it will be clear is not really viable. Something needs to change. Another consideration that's starting to become increasingly more important in view of things like climate change is that also for LoFar, when you think about the energy consumption that we invest in data reduction in storage, it basically adds 66% to the carbon footprint of each single LoFar observation. Basically, what I'm saying is that the energy consumption of storage and compute is getting to similar levels as the energy levels required for just running the telescope. So all in all, we need to start rethinking a few things. So our starting point is basically a software stack that we have developed and maintained at Aston. Core key components are the DP3 package, which is a streaming framework mainly used for calibration. Can do all sorts of calibration. There's dependent, there's independent, applying a wide range of constraints to the solutions while solving. And the other key package is WS Clean, which is a well-known imaging package used also for imaging with many other telescopes around the globe. And under the hood of these packages, there are a number of core dependencies like FreeBeam, the former LoFar beam, which we have extended to support also telescope beams for other telescopes. AO flagger was already mentioned a couple of times. The image domain gridder, which is a screen-based imager instead of a fast-based imager. And recently introduced Radler, which stands for the Radio Astronomical Deconvolution Library. It basically contains the deconvolution functionality formerly included in WS Clean, now available as a separate library for image-based deconvolution. You see that many of these blocks are tagged with 3 possible tags. Python means that there is a pip package available, so you can do something like pip install dp3, and then you can make do dp3 stuff from Python. CLI means command line interface. Well, I think that is clear enough. And the tag C++ means that that these things can be compiled to a shared library object that you can link your own program against to use the modules available in that library. So how well does this perform? So for a reference, we picked a low-for HPA observation. Actually, it's one of the flanking field of an UR observation around the North Celestial Pole. 12 megahertz wide observation. As hardware, we used the DAS6 supercomputer at Astron, where we used a single node with 2 Intel Xeon E5 CPUs. It had 40 cores per CPU and 256 GB RAM available. To keep the test reasonably fast, we used the first 3 cycles of the Raptor pipeline, which use only 20% of the data. So basically, it captures time chunks across the data sets to reduce the data volume to 20%. The idea being that initially you have a poor calibration, so you won't be able to achieve this thermal noise anyway. So the Raptor pipeline is configured to initially process on 20% of the data, and only in the last cycle get to 100% of the data, getting to the full depth of the image. Well, here you see the time for calibration imaging. What you see is that the calibration grows up every cycle, and that is because of the predict stage in calibration, because in your self-calibration process, your sky model becomes increasingly complex. And to the contrary, image is reasonably stable because you have the same number of visibilities and the same image sizes all the time. Let's see whether I can progress this. So we over the year we try to improve on that performance. Obviously, calibration can be parallelized over time chunks. The rationale being that you want to keep the frequencies together when you're doing a low frequency observation, because you want to apply, for example, a tech constraint to deal with the ionosphere, basically. While if you look at how the gains behave over time, there's not necessarily a mathematical relationship between the gains of a telescope right now and the gains of a telescope and the ionosphere, say 2 hours down the line. So you can pick the time chunks across the observation and basically do product those embarrassingly in parallel. And as you will see in a moment, that works quite well. Imaging is slightly more complicated, but you can usually parallelize over frequency chunks. Even if you want to make a continuum image at the end, if you have a large bandwidth, you probably want to do some chunking and frequency anyway, because you are interested in spectral index information. That means that a lot of the compute-intensive tasks like gridding and degridding can be done per frequency chunk, and that's only quote-unquote during, for example, deconvolution. You want to keep stuff together so you can make tailored term images and the like. So in order to coordinate all of that, we transformed WSLean. Formerly, we had basically multiple WSLean processors running on multiple nodes. We now have a single WSLean process using multiple nodes, where the stuff is coordinated under the hood. We're using MPI. One thing that allowed us to do is to basically write the WSLean scheduling in such a way that it has a fixed frequency to compute node map. So we can basically enforce that the work for a specific frequency chunk goes to specific nodes, and that enables further optimizations on, for example, the I/O to that node. You avoid multi-node locks on the data set. So there are a couple of things that you can do to improve the performance from there. Another thing that we do is basically reuse of model visibilities. So one thing that we see in low observations is that because the ionosphere, phases tend to vary on a reasonably short time scale, order of say tens of seconds, while the amplitudes of the antennas are fairly stable. As a result, people put in constraints that say, okay, I want to, I assume that my phases have a time cadence of say order 10 seconds, while for the amplitude it's more like minutes. And as a result, that tends to become two different time steps. Immediately put consecutively after one another. But that's in the same self-calibration cycle. So you're predicting exactly the same visibilities, the same complex numbers. The only difference being that in the first stage, you pick the phase of the complex number. In the second case, you pick the amplitude of the complex number. But you're predicting exactly the same numbers twice. And since predict is the most costly step of calibration, that was not convenient. So what we did is we introduced a method to basically configure the pipeline to, if there was a second calibration step, without a model update of the source model in between, it would buffer all the predicted visibilities and pass those along to the next step so that the predict can be skipped. So that's a very nice improvement. It worked quite well. Image-based predicts. The disadvantage there is that that for each limited time and frequency range, you have to do the whole fast Fourier transform of the image plus the degridding for a relatively small number of visibilities. And that means that, also to our surprise, direct predict turns out to be reasonably efficient until you reach the really elaborated source models, where we have really elaborated. I'm talking about, say, of the order of 40,000 source components with the gridder that we currently use. Also, in terms of gridder choices, there may also be some optimization possible. But that's about our threshold at the moment, which basically for us means that we can do this at the final cycle, for example, where we are sometimes up to 100,000, 150,000 source components. But in the earlier calibration cycle, we don't gain. Another nice improvement was that because the beams are quite stable and the Earth is rotating quite slowly, with respect to the size of the beam, you don't need to evaluate your beam pattern for every frequency channel and every timestamp. And instead, so we made that configurable, keeping basically the beam prediction solutions for, say, 2 minutes, for example, instead of evaluating the beam every second. So that also obviously saves a lot of computation, in particular when your beam model becomes more elaborate, like EM models for the SVA represented by spherical harmonic coefficients. So putting this all together, 1 year down the line, we have some new benchmarking results. So for your convenience, I have listed also the results shown earlier in the table as well. And as you can see, the parallelization in calibration works really well. Together with the optimization to reuse model visibilities, for which you benefit from cycle 3 onwards. Unfortunately, it didn't work out that well in imaging, and that are a number of reasons for that. And one is that there's a large fraction of serial code, which I'll show you in here. So these are the CPU usage statistics in the last 2 cycles of the Raptor pipeline. So you see first a bit. Let me see whether I do have a pointer. Does this work? Otherwise, I try to describe it. So on the left side, you see a small chunk where the CPU usage is pretty high. That's the calibration. It works very well. You see that all 3 nodes are occupied. Then there is a period where WS clean is working. You see a spiky pattern where there are spikes that all 3 nodes are active. This is the gridder and degridder stages. And then there is a stage where mainly the main node is active. And that's the deconvolution stage of the major cycle, the image-based deconvolution stage, which is still a single node process. So then basically the worker nodes are waiting until the next major cycle of the major imaging cycle is starting. And then there is this surprisingly large gap in which nothing seems to be happening. And that's a single Python script using PyBDSF working on a single thread out of your 120 threads available to filter the sky model. And that's obviously clearly room for improvement there. But because they have large serial components, you can help speed up the imaging process, but you don't gain much. So those are obviously clear targets for improvements. So what's the challenge in imaging? So the gridding, degridding, imaging major cycle part. If you run this on a multi-node system, then all these worker nodes will start requesting data from your storage nodes at the same time. In many systems, that poor storage node has quite a challenge to keep up with that. So we're currently working on a scheduler that basically tries to read data once and then define all the tasks related to that data, for example, all the facets related to that data, and then offloads that so that the data is read fewer times when you do facet imaging, for example. We also try to overlap I/O and computing work. Another optimization which we can try thanks to this frequency to node map is to basically store the data for each frequency locally on the compute node instead of keeping it on a storage node. The next last bullet is this improvement of source model filtering. Somebody's already working on that to basically improve PyBDSF. And in the end, somewhat longer term, we want to use accelerators to improve the gridding, degridding performance in particular. Other improvements that we are currently working on is baseline independent averaging. So in DP3, it's possible to work with baseline independent average visibilities natively. You can, if you use a DP3 as a solver for your calibration, it will solve directly on the BDA's visibility. It won't expand them first to full resolution, like for example a tool like CASA would do. Currently we've been trying to make WS Clean BDA proof as well, so that the entire pipeline can operate on BDA's visibilities. We're also working on smearing corrections, so that our predictions, visibility predictions in, for example, the major imaging cycle, but also in the calibration prediction becomes more accurate. And like I said, we're working on accelerators. So that brings me to my summary. So we started out from a code base that already offers many advanced methods for calibration imaging. So in terms of functionality, we think we have the stuff needed to do the calibration imaging for telescopes like LOFR and SDA. We are focusing now on making that more efficient, more scalable, and the like. We already managed to make some nice strides forward, but we are currently continue improving, and we have some ideas on the table. Thank you.
Questions?
Thanks, Stefan. Really interesting talk. I think LOFAR uses Disco for visibility compression in the archive. Is this also used while you're processing the data as well?
No, we don't have methods that work natively on Disco compressed data like we have with BDA. So when there is a Disco compressed data set in the archive, we first unpack it and then start processing it.
Yeah,
but we are using now, there's a project, the LDV project, as we call it, LOFAR data valorization. where we are basically running a standardized pipeline, applying disco compression to our existing data set to which disco compression not has applied. Because part of the big cost that we are paying on an annual basis is for storage. Currently, Aston has the honor of hosting the largest radioastronomical archive on the planet with 60 petabytes of data. Yeah, that starts to become expensive, but obviously we will probably soon be dwarfed by the SDA in terms of that data site.
Yeah, so I've been thinking a little bit about compression and working with Richard Dobson, who's working in this area. A couple of points he's made. First of all, if you can sort of integrate it into your data processing, then it can actually, there's the compression and well, certainly the decompression, but also the compression is very, very cheap computationally. So if you're certainly if you're IO bound, then working with compressed data the whole time speeds you up considerably. If you're having to juggle things because you don't have enough memory, then of course having everything working on compressed data sets also helps with that as well. So you can imagine you know, multiple things being done on the same node where you're interleaving when one node is using the CPU and when the other one is.
Right.
That can be tricky if you don't have enough memory to deal with one data set at a time. And the other nice thing about compression, if you do it on the compression ratio on a baseline dependent basis, you kind of get something very close to BDA for free, but you keep the nice property where you have the same number of time steps per baseline, but you're just changing your compression ratio. So your information content is similar to doing BDA, but you're keeping a data set where you have similar numbers of visibilities on each time step.
Yeah, that could be indeed of interest in the context of the X-Radio projects. You probably have heard of that one. So it's the new aim to be the successor of the Mexican set format. And there they want to, what I heard last time was that they plan to use the X-Radio library, which is compatible with stuff like Xtensor and NumPy arrays. And then indeed, having a fully regular tensor would really be helpful.
Yes, but really interesting to hear about all the stuff you're doing. Thank you very much.
Thank you. Well, I guess we'll come to the one here.
I know it's late in the day. Thanks for a very nice talk. Yes. You mentioned at the start of your talk that you're also looking at the SK-low data pipeline. So from that perspective, I just wanted to mention a very different use case. And this is all, of course, very interesting and I realize very challenging. I look at the sun. So we want to make images essentially every time slice, every frequency slice. So we don't have a lot of visibilities to deal with. For us, the problem also becomes effectively narrow field of view or small field of view because the sun dominates the power and the visibility so much that we don't have to, image all the way out to the edge of the wide field of view of SK-low.
Sure.
So I just wanted to sort of plant that thought that somewhere in the SDP processing, this has to be taken care of because I have no clue at this moment as to where it stands in the SDP processing pipeline, if there is a solar mode or not, or because the SDP is not supposed to give any visibilities, right? It's only supposed to give images. So we do need critically a mode which will deal with the solar imaging aspects. So just wanted to sort of.
Yeah, good thing to flag. So at this point in time, I'm not aware that there is work on solar imaging pipeline plans. But from LoFar experience, I know that sometimes visibilities can be quite handy because with LoFar we have also done imaging of the sun and of the moon. And one of the challenges there is that they don't move at the sidereal rate for which all the software is usually developed. So that also required quite some additional work. I know that there are people in LoFar currently studying the sun. They basically use the tight array beam modes. So they basically cover the whole sun with tight array beams and basically use that as a kind of imaging mode for the sun.
Because you're imaging every time slice, the non-sidereal motion doesn't really bother you because you're imaging every second or half a second or something like that. So that is not as much of an issue. The fly's eye mode has been used in the past, but I think the LOFAR group has also gone to imaging, more conventional imaging rather than the fly's eye. Thank you. Thank you, sir.
Thanks, Stefan.
Welcome.
And thanks, everyone. Let's thank every speaker in the session. Yeah, thank you, everyone, for making a fantastic program. And I guess that's the end of it. And see you all in Krakow.
And that is leadership, putting yourself in the end. Oh my, well, that was quite appropriate. Yeah, fair enough. So I'm with a lot. Yeah. All right. Thank you. Oh, yes, and you should next year. That's far apart. Yes, not a place like too much apart. That's nice one. Yeah, the last question I could edition was it's a really crucial one. For me, this was SDI was well, no, I mean, I've got it. Yes, so you discuss the sort of schedule about this. Yes. Well, I think she just misunderstands. It's a lot of yes, toleration. Radio yeah, it pushed me both. I should possible that very last processes. It's useful, but it's not quite okay. All right. It's not about maximum, but social science. Yeah, right. See you later. See you around. Hey.